So welcome, Joachim. This is the first lecture on sterile neutrinos, right? So
the first lecture of the last lecture. Okay, yeah. So thanks a lot for inviting me to the organizers, and thanks to all of you for still being here on the penultimate day of the school. So I'm going to introduce the last dark matter related topic that we're going to talk about at this school, and that's the physics of sterile neutrino dark matter. So the plan of the lecture is we have today and tomorrow. Today we're going to talk about the more formal aspects. We're going to talk about what sterile neutrinos are, and most importantly, how they would be produced in the early universe if they were a dark matter candidate. And then tomorrow, we're going to talk about detection prospects and some interesting anomalies that have appeared in this context. Right. So just to give you a very basic overview of what sterile neutrino dark matter is. So you know what neutrinos are? But the remote participants can hopefully hear me.
yeah.
Okay. Otherwise, they will hopefully complain through the chat. So we know that in the standard model, there is 3 flavors of neutrinos. They participate in the weak interactions, but no other interactions than that. However, the possibility is not excluded that there's more than 4 neutrinos in nature. What is excluded is that there is a 4th species of neutrinos that is light and couples to the W and Z bosons. So when we talk about sterile neutrinos, what we effectively mean is a fermion beyond the standard model that is a total singlet under all standard model gauge groups. Some people call them sterile neutrinos, others call them heavy neutral leptons. It's all the same thing. It's just a standard model singlet fermion. The reason they are sometimes called sterile neutrinos is because being a total singlet, they can mix with the active neutrinos. So the active neutrinos can oscillate into them. They can be decayed between different species, the sterile ones and the active ones, but we'll see all of that in more detail in the course of the lecture. But because neutrinos are the only fermions that can more or less directly talk to a singlet fermion, that's why these singlet fermions are often referred to as sterile neutrinos. Yeah, so what we're going to do now is that we're going to look at the coupling structures of neutrinos and sterile neutrinos in more detail. And then we're going to talk about how these couplings can be exploited to produce hypothetical sterile neutrinos in the early universe. And just to give you an idea, the mass range that we are typically talking about here is maybe order keV or so. So these are still much heavier than the standard model neutrinos, but much lighter than, for instance, WIMP dark matter or so. So the reason we are talking mostly about the keV range is not because that's particularly favored from a theoretical point of view, but because it's favored from an observational point of view. But we're going to see that when we talk about constraints. But just keep in mind that the particles we're going to talk about here are going to have masses of order keV or so, if they are dark matter candidates. Okay, so for the things that I'm going to write down, I'm going to apologize that I'll sit down because it's just much easier to write while sitting down. So we're first going to talk about neutrino masses and mixings, starting with the standard model and then very soon introducing the sterile neutrino. So in the standard model, the relevant couplings of neutrinos are contained in the following Lagrangian. There is a sum over the 3 neutrino flavors. And then there's one term that couples neutrinos to the W boson. So there is a G over square root 2. G is just the SU2 coupling constant in the standard model, so the gauge coupling of the weak interaction. The coupling is mu alpha L bar, gamma mu, nu alpha L, times the W mu plus field in this case, plus Hermitian conjugate. So there is a left-handed neutrino field, a Hermitian conjugate left-handed neutrino field, and a W field. Now, as you know, what field operators do is they destroy particles and create antiparticles, while complex conjugate field operators create particles and destroy antiparticles. So this term here describes, for instance, a process in which a neutrino comes in and a neutrino goes, a charge, sorry, this shouldn't be a neutrino field, of course, this here should be a charged lepton field, so E alpha L. So what this describes is, for instance, a process in which a charged lepton comes in, a neutrino goes out, and a W boson goes out. So diagrammatically, something like this. There's here the charged lepton field, here the neutrino field, and here the W boson. Then in addition to the charge current interactions, there's also the neutral current interaction. To go. The neutral current interaction is plus G over 2 cosine theta W. So theta W is just the Weinberg angle. This just describes the fact that neutral current interactions have a slightly different strength from charge current interactions. Mu alpha bar L, gamma mu, mu alpha L, Z mu. And this time, this is now really an interaction between neutrinos. So diagrammatically, that's a diagram with a neutrino going in, a neutrino going out, and the Z boson. Notice that I've been careful about putting flavor indices here. In principle, I should probably also have put a sum over flavors here, but as usual, of course, summing over repeated indices is implied. And these flavor indices are essentially defined by this first interaction here. So the neutrino that couples to the electron is what we call the electroneutrino. The neutrino that couples to the muon is called the muon neutrino, and the neutrino that couples to the tau is called the tau neutrino. That's how this flavor is defined. Well, finally, there's not only interactions, there's also a mass term that's important. As you know, neutrino masses would be a topic for a separate lecture. So for simplicity in this lecture, we are going to assume that neutrinos have simple Dirac mass terms, similar to the masses in the standard model. So we assume that the mass terms have the form mu alpha bar L, mu beta right, plus Hermitian conjugate. And this field, which we call nu beta right here, that's a new type of field. So in a sense, this is already a field beyond the standard model. The vanilla standard model, the way Steven Weinberg wrote it down, only has left-handed neutrinos and therefore would not admit such a term. But if we want neutrino masses, then there must be some right-handed state. So for simplicity, we're going to introduce this right-handed state just as a new state. One can write down models where this right-handed state is, for instance, just the complex conjugate of the left-handed fields. That would be a Majorana neutrino mass term, but we won't have time here to really go into the details of neutrino mass generation. Therefore, we are doing the simplest thing, namely just a extra right-handed state. And notice that, so this term, of course, is supposed to be generated from a Higgs mechanism. So that means at the SU2 invariant level, so this would come from an operator of the form some Yukawa coupling alpha beta times nu alpha times L bar alpha times nu alpha right times I sigma 2 times the complex conjugate Higgs field. Just a standard Higgs Yukawa coupling in the standard model. But at the SU2 invariant level, the neutrinos are, of course, part of SU2 multiplets. That's why above the electroweak scale, we are not writing the neutrino here, but we have to work with SU2 doublets. For our purposes, as I mentioned, the mass scale that we are interested in is KeV. So we are interested in an effective theory in which electroweak theory is broken. So we're going to treat the neutrinos and the charged leptons as basically independent degrees of freedom. We don't need to worry about the fact that they are from the same SU2 doublets and are somehow related. Yeah. But if you look for a moment at the term in the SU2 invariant UV complete theory, so you have here this SU2 doublet containing the charged leptons. You have here the Higgs doublet. And this already shows you that the right-handed neutrino field has to be an SU2 singlet. If you do the same exercise considering the hypercharges, the Higgs doublet has a hypercharge of -1. L also has a hypercharge of -1. So the hypercharges of L and H also add up to 0, which means that the right-handed neutrino field can't have a hypercharge either. So these right-handed neutrino fields are already essentially sterile neutrinos. They are standard model singlet fermions. So by definition, they are sterile neutrinos. Now here at this level, we are trying to explain the phenomenology of the standard model. So for this, the right-handed neutrinos would have to have the same mass as the left-handed neutrinos, just the same way that right-handed charged leptons and left-handed charged leptons have the same mass. But in principle, here we are already encountering what we call a sterile neutrino. Now, when we want to introduce a sterile neutrino as a dark matter candidate, what we will do for simplicity here is we are going to introduce an extra particle, which we call nu s, and we're going to assume for simplicity that this nu s also has a left and right-handed component. So we're going to work with Dirac fermions throughout. That's not necessary, but the phenomenology will be almost the same. So we introduce a new species, which we call nu s left, plus its right-handed partner, nu s right. And all of them are supposed to be total singlets under the standard model. Singlets under SU3 cross SU2 cross U1. As I mentioned before, because they are total singlets, yeah.
Are right-handed neutrinos themselves, like the normal right-handed neutrinos, are those also a dark matter candidate?
Typically, their masses don't work out.
Okay.
So if you, in the scenario that I wrote down here, the right-handed neutrinos would have the same mass as the left-handed neutrinos. In more elaborate neutrino mass models, for instance, the seesaw mechanism, the right-handed neutrinos sit at a very, very, very heavy mass scale, like 10 to the 14 GeV or so. And that would mean in particular that they would decay almost instantaneously through, if nothing else, they would decay via their small mixing with the active neutrinos. They would decay to 3 active neutrinos, for instance. So they would be gone almost instantaneously. So they would not be able to survive until today. That's in fact already one of the advantages of the keV scale. It's marginally sufficiently heavy to account for cold dark matter, but it's already sufficiently light that the lifetime is extremely long. So the lifetime can far exceed the age of the universe. But the lifetime scales with the 5th power of the mass. So as you go heavier, the lifetime very rapidly drops down to very short time scales. Okay, so because they are total singlets, these extra neutrino states will not be able to couple to the W and Z boson. So the only effect they're going to have from the above Lagrangian will be on the mass term, the modified mass term. Then is basically the mass term from above, except that the sum now runs over 4 instead of 3 flavors. So this now runs over E, mu, tau, and S. Other than that, it's unchanged. Mu alpha L bar, mu beta right, plus Hermitian conjugate. Now let's talk about this mass term in a little more detail. You notice that we have 2 flavor indices appearing here, alpha and beta. And in fact, this matrix M is just a general complex 3x3 matrix in the standard model, 4x4 matrix when we have 1 sterile neutrino. So this means in particular, it has off-diagonal entries. So it leads to mixing between different flavors. And this mixing is, of course, what most of neutrino physics is about. So M alpha beta is a general complex 4x4 matrix now. And this means we can diagonalize it, and we need to diagonalize it if we want to know the masses of the physical state. So a physical state that propagates through space and time has to be a state with a definite mass. So we need to determine the eigenvalues of this mass matrix. The way this is done for such a general matrix is we're multiplying from the left with a unitary matrix U, from the right with a unitary matrix, which we call V dagger, and we obtain a diagonal matrix. So this one here is a diagonal 4x4 matrix, and V and U are unitary. The reason these are two different matrices is because we can transform the left-handed states and the right-handed states independently in flavor space, right? So we can apply a unitary rotation to the new R fields and a completely independent unitary rotation to the new left fields. And that's how we end up with this diagonalization prescription. We call this diagonalization in physics, a mathematician would call it a singular value decomposition. Yeah.
I think I'm just forgetting my linear algebra here, but would we get the same? Oh, thank you. Would we get the same matrix in the end if we did U dagger MDV instead of U MDV dagger?
You would get the same mass matrix, yes.
Okay, got it. So it doesn't really matter which direction, I guess, we rotate
It doesn't matter.
our right and left field. Okay, thank you.
Yeah, what I should have said, this diagonal matrix by definition is not only supposed to be diagonal, this is also supposed to be real. And thereby, if you call U dagger and V dagger, well, you've just renamed your matrices in a sense. So now what this does to the fields is we now have the so-called mass eigenstate fields. And I realize there's a typo in my preliminary lecture notes, which I still have to fix. Oh no, it's not a typo, no. So the mass eigenstate field nu J, so Roman indices, Latin indices usually refer to mass eigenstates, Greek indices refer to flavor eigenstates. So the jth mass eigenstate is given as sum over alpha U alpha star times mu alpha left. And similarly for the right-handed fields, but because the right-handed fields don't interact with anything, we're usually not so interested in the right-handed fields. Okay. Now, in principle, we could now go ahead and plug these rotated fields here into our Lagrangian, and we could write down the Lagrangian once again in the mass basis. What we would then see is, if I may quickly scroll back up to the Lagrangian, the term containing the neutral current interactions, so this one here, that will not change at all, because there will be the new alpha left fields will be multiplied by U dagger, the new alpha left bar fields will be multiplied by U, so there is a U times U dagger appearing, and that is, of course, it's just the unit matrix. Well, the mass term will now be diagonal, of course. What will change is the couplings to the W boson, because with these unitary rotations, we are changing the neutrino fields, but we are not changing the charged lepton fields. So what we're effectively writing down now is an interaction of an electron to a new 1 mass eigenstate, an interaction of an electron to a new 2 mass eigenstate, an interaction of an electron to a new 3 mass eigenstate. So diagrammatically, this implies the following. So inserting this into L. So what we end up with as interactions is now an interaction, for instance, between an electron and a new one with the W boson. This one would be multiplied by UE1 star, the way I've written it up there, plus the same interaction of an electron with a new 2. This vertex would now come with a UE2 star plus an interaction with a new 3. UE3 star. So in a sense, when I have this, this type of interaction, imagine, for instance, I have a W boson decaying via this vertex. So W boson going, say, to a neutrino and a positron. Then what I'm effectively doing now is I'm creating a superposition of these 3 mass eigenstates. In flavor language, we would say, well, the W decays to an electron and an electron neutrino. In terms of mass eigenstates, this means W decays into the positron plus a new 1 mass eigenstate superimposed with a state that consists of a positron and a new 2 mass eigenstate superimposed with a state that consists of a positron and a new 3 mass eigenstate. So when we're making a neutrino, we are always making this superposition. And that's interesting because, as I mentioned before, neutrinos, the rules according to which neutrinos propagate are governed by their mass, not their flavor. So now I have created a superposition of 3 mass eigenstates that all propagate in a different way. And this is at the origin of what's known as neutrino oscillations. And that's what we're going to talk about next. So that will be, oops.
And then shouldn't I have a fourth diagram with some kind of sterile neutrino?
Oh yeah, right. Because we're already in sterile neutrino world. Yes, of course. I was still biased towards the standard model. Yes, sorry about that. This would now be U4 with a UE4 star. And for phenomenological reasons, this mixing between the active and sterile neutrinos needs to be small. So all matrix elements that have either a subscript S or a subscript 4 are necessarily relatively small. But nevertheless, they are in general non-zero. Okay, yeah.
So I think you just implied that our sterile neutrino is intrinsically linked to our 4th mass eigenstate.
For phenomenological reasons, yes. So the 4th mass eigenstate is the mass eigenstate that has the largest overlap with the with the sterile flavor eigenstate. So you can imagine. So each mass eigenstate has different admixtures of the different flavor eigenstates, and vice versa. Each flavor eigenstate has different admixtures of different mass eigenstates. And for phenomenological reasons, the 4th mass eigenstate has the largest admixture of nu s. So for instance, the way this is often drawn is, for instance, the following way. So you draw a bar that like represents the full neutrino state, and then you divide it up into individual regions that are, for instance, nu4, nu3, nu2, nu1 or so. Now this is just a sketch, this is now not real parameters, but it suggests that the mixing between nu s and nu4 is very large, whereas the mixing between nu s and the other mass eigenstates is relatively small.
And then just a follow-up question, if that's okay.
Yeah, please.
So couldn't your 4th mass eigenstate be very close to one of your other mass eigenstates, and therefore, like, I don't quite understand how that little schematic is determined.
I would say this little schematic, these are the 3 parameters of nature. So in principle, you're right. There's nothing wrong from a theoretical point of view with the fourth mass eigenstate being very close to the other three. But at the moment, we have some theories, but we have no proven theory to explain the values of these parameters. So for the moment, we need to treat them just as free parameters of nature that we need to measure. In much the same way as the elements of the CKM matrix are not yet derived from any fundamental theory, but are just determined phenomenologically. But in principle, you're right. Typically, once again, for phenomenological reasons, we consider the case where the sterile neutrino has a mass that's very different from the active neutrino masses. But from a theoretical point of view, there's no reason to do so. From a theoretical point of view, they could all be very similar in mass.
Got it. And if they were all very similar, then we might not be able to say that we have a lot of overlap between the sterile neutrino flavor state and the fourth mass eigenstate.
That then depends on the mixing angles. In principle, you could have 4 mass eigenstates that are all very similar in terms of their eigenvalues, but are still come with very small mixing angles. One can argue that this is maybe not a natural thing to expect, because in that case, renormalization group effects will typically drive the mixing angles to larger values. But at this level, I would say that would be okay. So there's no a priori correlation between the masses and the mixing angles.
Okay, thank you.
Okay. Any further questions at this point? If not, then let's move on to neutrino oscillations. So neutrino oscillations. The reason we are discussing neutrino oscillations here is not because I want to go into the physics of Dune and hyperkamiokande, but because neutrino oscillations are the mechanism through which sterile neutrino dark matter would be produced in the early universe. Okay. So the basic idea is that we have some neutrino source that makes a neutrino flavor eigenstate. The only way we can make neutrinos is through the weak interaction. The weak interaction makes a neutrino flavor eigenstate, and that flavor eigenstate is a superposition of mass eigenstates. So we start with a flavor eigenstate. Start with flavor eigenstate. I'm writing this in bracket notation. So nu alpha is equal to sum over j u alpha j star times the mass eigenstate nu j. Right, so I'm just saying that the state that we have produced is a superposition of mass eigenstates, just as described in the diagram above. Notice that this is a u alpha j star here, whereas the corresponding expression for the fields, for the mixing of the fields, contained a nu alpha. That sometimes causes confusion, but it's essentially related to the fact that a ket state is obtained by acting with the complex conjugate field operator on the vacuum. So you want to make a particle, so you don't use the field operator, but the Hermitian conjugate field operator. And the Hermitian conjugate field operator transforms with the Hermitian conjugate of the mixing matrix. But that's only a minor point in case that causes confusion. Okay. Now, there's various ways of proceeding from here. We're going to do the simplest thing. We are going to assume that this neutrino has a reasonably well-defined energy and momentum. And so during propagation, what will happen is that this state acquires an oscillatory phase factor. So propagating this state through space and time, propagating over distance L and time t. And this state turns into, let's call this nu of t, comma L. I'm not going to give this state a flavor index anymore, because we will see that oscillations lead to a change of flavor. So basically, this is still a sum over the 3 mass eigenstates. After they've been produced, they don't know about each other anymore, so they evolve independently. But each of them acquires a different phase factor, because each of them has a different energy and a different momentum in general. So, please.
Thank you. Is there not kinetic mixing between the states? He said they don't see each other anymore, but
The kinetic, the kinetic terms of the different states are independent.
okay.
I haven't written down the kinetic terms in my Lagrangian. I can do it as a side note here and then erase it again. So the kinetic term would have the form sum over alpha nu alpha bar L I times d slash nu alpha L. And I can write this equivalently in mass eigenstate notation, sum over J nu J L bar I d slash nu J L. Once again, because when I transform the field nu alpha with my unitary rotation, the way I transform nu alpha is with u, the way I transform nu alpha bar is with u dagger. So u and u dagger cancel to the unit matrix. And therefore, the kinetic terms of the different mass eigenstates are completely independent. There's no kinetic mixing. There is mass mixing. So if you had a non-relativistic neutrino, then the left and right-handed states would mix with one another. But first of all, neutrinos are rarely non-relativistic. And second, that would still not lead to any change in flavor. Okay. Move this again. Use the maximum number of undo steps, so we didn't need to do it by hand. Right. Now, if we detect the neutrino state at a later time, detection is again a process that has to proceed through the weak interaction. So it is a process in which we carry out a flavor measurement. The way we typically detect neutrinos in a flavor sensitive manner is through a charged current interaction. So we allow them to interact with an atomic nucleus, for instance. They make a charged lepton, and we're able to identify the flavor of that charged lepton. So neutrino detection via ACC interaction implies projection onto a flavor state nu beta. Projection onto flavor state nu beta. So, oh, and this nu beta, of course, can again be written in terms of mass eigenstates. So that's then u beta j times nu j, and I'm omitting the sum over j now because I will be writing down a lot of sums. Okay, so let's do this. We form the scalar product of the bra vector nu beta and the ket vector nu alpha. No, not nu alpha, the time evolved ket vector nu of t and L. Okay, sum over j and k. There is the matrix element from the definition of our initial neutrino state, u alpha j star. There's the matrix element from the definition of nu beta, u beta k. There is the complex phase factor that the neutrino has acquired while propagating. And there is now a scalar product of nu k and nu j. And because these are orthogonal states in the Hilbert space, this nu k times nu j scalar product here reduces just to a Kronecker delta in k and j. So one of the sums gets eliminated and we end up with just nu j, u alpha j star, u beta j times e to the minus I e j times t plus I p j times. Okay, that's the oscillation amplitude. Typically, we're also interested not in an amplitude, but in a probability. So we want to know what's the probability that a muon neutrino that I make has oscillated into an electron neutrino after it has propagated. So we need to take the modulus square of this expression, oscillation probability. That's typically called P alpha beta. and is just the squared modulus of the state above. So writing this out, we get the two matrix elements from nu beta times nu. Then from multiplying with the complex conjugate of the amplitude, we get two more elements, which is then u alpha k, u beta k star. And now we get the complex phase factor Ej minus Ek times T plus I Pj minus Pk times L. Okay. Now we still have this dependence on space and time, and that is something we would like to get rid of. And so we exploit the fact that in a typical neutrino oscillation experiment, we are not able to measure the propagation time of a neutrino. We know pretty much where our source and where our detector is located, but we typically don't have enough timing information to be able to tell exactly when a neutrino was made and exactly when it has been detected. So we can integrate over the time. So typically, T is not measured with sufficient precision. Therefore, we define an oscillation probability that depends only on the propagation distance. We need some normalization factor, and we integrate over T. T alpha beta of T and L. Set this N here, this is just a normalization factor. So we can do this integral explicitly. Formally, it leads to a delta function in Ej minus Ek. That is not a huge problem because that delta function, well, it's never going to be an exact delta function because the integration, the time interval over which we integrate is always going to be finite. It's just a very strongly peaked function, and the normalization of that function can be absorbed into the normalization prefactor here. So let me write this down and then we'll go through this argument again. So this becomes 1 over n, sum over jk of our 4 matrix elements, which I copy from above, u alpha star, u beta j, u alpha k, u beta j star. There's this delta function in Ej minus Ek. And what that delta function does is, well, it essentially forces the neutrino states that interfere with one another to have equal energies. And in that case, we can express the momenta in terms of the energies. So the remaining complex oscillating factor now becomes an I times square root E square minus mj square minus square root E square minus mk square times L. Right? So once again, what we've done is we have argued that we are either not measuring the propagation time sufficiently accurately, or we are just discarding this information. We are ultimately maybe interested only in an energy spectrum. So we are integrating over a long observation period of maybe several months or so and lumping the data together. Yes?
So what we just did, we said that neutrinos are only able to interact with each other if they have the same energies. That's only true over this time averaged window, right? In individual reactions or individual interactions, the neutrinos can have different energies.
We'll come to that in a moment, but in principle, yes, as long as it's allowed by the Heisenberg principle.
Okay.
So in principle, of course, states, well, states can only interfere with one another if the experiment is not able to distinguish that there are different states. And this translates into, in particular, your energy and momentum resolutions being sufficiently poor that you cannot tell different neutrino mass eigenstates apart. And so within this uncertainty that the Heisenberg principle grants you, you can have different energies interfere with one another. I'll go into a bit more detail on this after we are done discussing the formalism of oscillations, because that's one of the important caveats that you mentioned, but that's an excellent question.
Thank you.
Yeah, there's another one behind you.
Okay. Hi. So it's you said that T is not measured sufficiently precisely, but I think it might be possible because Oprah, ages ago, Oprah said they could measure the scale of like neutrinos, right? So it means that they have to that there exists a way to measure T somewhat precisely, even though it's like super troublesome. I mean, it's super troublesome, right? But if measuring T precisely enough allows me to probe something interesting, that then I will go through the trouble of.
I was wondering if someone would ask that question. I'm very happy that you did ask that question.
Okay.
Because it's a very good point. Indeed, in a neutrino beam experiment, you do have excellent timing resolution because the beam spills that make your neutrinos are relatively short. And well, they're traveling at the speed of light, so you know exactly when they're supposed to arrive at the detector. And typical electronics may allow you to do maybe nanosecond timing or so. The thing is, in order for this approximation that I'm making here to become invalid, the timing precision that you would need, let's see, it would need to be better than the inverse difference of the different energy eigenstates. Now, the different energy eigenstates have typical so the typical energy differences between the different mass eigenstates are of order delta m squared, so the squared mass difference between the different neutrino mass eigenstates, divided by the neutrino energy. In a neutrino beam experiment, you have GeV neutrinos. The mass squared differences in the standard model are, the largest one is order 10 to the minus 3 electron volts. So this delta EJ, let me write this down once again as a side note here. So EJ minus EK is similar to delta M squared over E, which is similar to 2.3. Well, let's not be super precise. Let's just call this 10 to the minus 3 EV square divided by a GeV. So that's effectively 10 to the minus 12 electron volts. So that translates into a delta T of 10 to the 12 inverse electron volts. Yeah, you're right. And this, I think, is only something like 10 to the minus 3 seconds or so. So not a particularly stringent requirement. The thing is, however, if you take this into account and allow for a larger time interval, a short time interval, good timing resolution, the funny thing is that you'll still get the same oscillation formula. It's a bit too cumbersome to show this because what you basically need to do is you need to actually compute this EJ and EK that you would get, for instance, from a pion decay. You would need to compute the PJ and PK, so the momenta of the different mass eigenstates that you get from pion decay. And what you find is that lots of terms in here between the EJ minus EK difference and the PJ minus PK difference, lots of terms cancel. And you'll end up with exactly the same expression as what I'm going to derive here.
Oh,
That-
okay. So essentially, even if I were to go through all the trouble to like not integrate this over by measuring it, there is no like extra interesting bits of physics that I can probe.
No, because in order to probe extra interesting bits of physics, you need to be able to measure both the energy and the momentum very, no, let me think. No, that's the opposite limit. This would be very poor time resolution where you measure the energy and the momentum very precisely. Then you'd be able to determine which neutrino mass eigenstate has been propagating. Here, you won't be able to probe any extra piece of physics, and that's because neutrinos are propagating nearly at the speed of light. So the reason that all these terms cancel is related to the fact that neutrinos are propagating almost at the speed of light.
Okay. Thank you.
Before you go on, there's a question online.
Yeah.
Yeah, okay, I'll read it out. It says, if I understand correctly, you're assuming Dirac neutrinos here. Are there any important differences compared to sterile neutrinos from the seesaw mechanism?
No, for oscillations, Dirac and Majorana neutrinos behave in exactly the same way. And the way to see this is look at this horrible product of mixing matrix elements here. The way the mixing matrix for Majorana neutrinos and Dirac neutrinos differ is that, so the mixing matrix for Majorana is the mixing matrix for Dirac multiplied by 2 extra phase factors. So you multiply with some matrix of the form E1, e to the I alpha, e to the I beta, where alpha and beta are the Majorana phases. Now this extra factor here, which is the difference between Dirac and Majorana, these factors will exactly cancel in this product of matrix elements up there. And therefore, in an oscillation experiment, you'll never be able to distinguish Dirac and Majorana neutrinos in principle. The only way to probe the difference between those is, well, via other methods that do not involve oscillations. Okay. Good, then I'll move the side notes again. And go back to this calculation. So what I'm going to do in the next step is I'm going to be a bit careless about this delta function and say that, well, its normalization is going to be absorbed into the normalization factor. So I'm going to drop both the delta function and the normalization factor. I'm going to start just with the sum over j and k with the horrible product of matrix elements. Beta j, u alpha k, u beta j star. And what I'm also going to do is these square roots here. There we can exploit the fact that neutrino masses are very small, much smaller than the typical neutrino energies. So we're going to do a Taylor expansion. And that Taylor expansion leads to the following, minus I times delta m jk square divided by 2e times L, where the quantity that we call delta m jk square, that's just mj square minus mk square. Okay. This is like the most general form of the neutrino oscillation probability. We are in a moment, we are going to make the simplification that we restrict ourselves to 2 neutrino flavors, because then it becomes much, much more transparent. But just to reiterate, what we've done is we've assumed we start with a neutrino flavor eigenstate. We propagate it in space and time using the fact that different mass eigenstates propagate differently. In particular, they acquire different phase factors. Then we've projected onto a flavor state, which we assume we detect. That gave us the oscillation amplitude. We have taken the square of that amplitude. And then we have, with somewhat shady arguments, we have essentially justified the assumption that all neutrinos have equal energies but different momenta. As I mentioned in response to your question, that's not a necessary assumption. And one can do much more beautiful and I would say more solid calculations that lead to the same formula in the end. You could, for instance, assume that the neutrinos travel with the same momentum, you would get the same result, but that would be even less justified physically. You could treat your neutrinos as wave packets. So you assume that your neutrino neither has a well-defined energy nor a well-defined momentum, but there's some smearing in both of them. And then you propagate those wave packets and allow them to interfere with one another. And you'll still get the same expression. You'll get some extra factors that describe effects like wave packet decoherence that our formalism here cannot capture, but they are typically negligible. What you could even do, and what in my opinion is perhaps the most beautiful approach to neutrino oscillations, is something that I want to briefly mention here without doing the calculation. It's again a wave packet treatment, but where you don't even treat the neutrino as wave packets, but you only worry about the states that the neutrino couples to at production and at detection. That way, we have completely avoided having to deal with fermions for which mass and flavor eigenstates are different, and all of that physics comes out of your formalism automatically. So more thorough derivation using wave packets. So we consider schematically a diagram of the following form. So let's assume there is some neutrino production vertex here. There is a number of particles coming in, whatever those are. Then you have your propagating neutrino. And then here on the detection side, there's again, maybe some particles coming in, some particles going out. And now the idea here would be you describe these external particles as wave packets. So describe the external particles or the neutrinos interaction partners as wave packets. Wave packets. And the neutrino is then just an internal line in a Feynman diagram. Internal line in a Feynman diagram. And then the whole physics of neutrino, yeah.
I think, Lindsay, did you have one?
Oh, yeah.
Okay.
Quick clarification of that last line. Is this supposed to be the normalization constant still?
So the question was whether in the last line of my equation there should still be a normalization constant. No, there shouldn't be, because this is already properly normalized as a probability. You can check this by summing over beta, for instance. So nu alpha to any flavor must have a probability of 1, and this expression satisfies that. So it is already correctly normalized. Yeah.
Oh, thanks. Thank you. And then with this next part here, are we assuming that our external states are relativistic species for the wave packet?
No, they could be non-relativistic. Doesn't matter for wave packet treatment.
Okay, all right, got it. Thank you.
All you're assuming in the wave packet treatment is they are somehow localized in momentum space and they are somehow localized in coordinate space. And how well you localize them, so how wide your wave packets are, that's essentially a free parameter that you put into your calculation. But the beauty of this formalism is, well, first of all, it's calculable, because if you describe all your wave packets as either Gaussian or Lorentzian wave packets, then all the many integrals that you need to do are doable analytically. But the most beautiful aspect is that the whole physics of neutrino oscillation and mixing is contained here in this propagator. It requires some work, because typically when we deal with Feynman propagators, we have in mind propagation over very short distances. So to get the oscillation probability out, we need to carefully derive an expression for a propagator of a particle that's propagating over a macroscopic distance. That can be derived from the usual expression of the Feynman propagator, but it's not entirely straightforward to do that. But then all the physics of oscillation drops out completely automatically. You don't put in any phase factors by hand or anything. It all comes out automatically. Okay, so that was just a side remark. At the level at which I have discussed this here, the only important thing is that we need to keep in the back of our minds that the neutrinos are effectively wave packets. So they have a non-zero spread in energy and a non-zero spread in momentum, because if all particles that were involved had perfectly determined energy and momentum, well, then we would have effectively determined the neutrino mass. And when we determine the neutrino mass, then we know which mass eigenstate is propagating. We would not see oscillations. So we are, in a sense, we are assuming that there's sufficient uncertainty that the different energy and mass and momentum modes can still interfere with one another. Typically, that's not a problem because, well, you know where your neutrino source is, you know where your neutrino detection happens. And from there, you introduce localization in space, which by the Heisenberg principle leads to delocalization in momentum. And that delocalization in momentum is already enough to enable oscillations. So for instance, when you're considering now once again a neutrino beam experiment, and you know, well, your neutrinos are produced in a decay tunnel that's maybe 100 meters long, and your neutrinos are detected in the detector that's maybe 50 meters long, that's already enough localization to allow oscillations to happen. Okay, now before we go back to more cosmological aspects of this, let me briefly simplify the oscillation formula for the two flavor case. So if we consider oscillations between only two neutrino flavors, then this formula can be greatly simplified, because in that case, the mixing matrix is just a 2x2 matrix, and the 2x2 mixing matrix is parameterized in terms of just one mixing angle. So it can be written as cosine theta, sine theta, minus sine theta, cosine theta. And if you take that and plug it into our general expression for the neutrino oscillation probability, then this leads to the following expression: P alpha beta 2 flavor is equal to sine square 2 theta times sine square delta m square L over 4e. I'm not going to derive that formula here, but you're highly encouraged to try it yourself. All you need to do is plug the 2x2 mixing matrix into the general formula for the oscillation probability that we derived above. So what this tells us is that the two fundamental parameters that appear in this limit, namely the mixing angle and the mass squared difference, they control the oscillation amplitude and the oscillation period. So the mixing angle, if we increase the mixing angle, then this prefactor will become larger, and that prefactor, well, that's just the amplitude of the oscillation. Controls oscillation amplitude. Now, the term that actually oscillates with distance is the term here that depends on delta m square. So delta m square controls the oscillation length. Okay. Yeah.
Is instantaneous oscillation theoretically possible, or do you need some finite amount of time?
Sorry, yes.
Is instantaneous oscillation possible, or do you need some finite amount of time to pass to have any probability?
You need a finite amount of. Oh, you mean long distance but short time? Well, you need time for the neutrino to get from point A to point B. What you could consider if you are, so imagine you manage to prepare a neutrino state that's extremely delocalized. So delocalization that's several hundred kilometers, for instance. Then you can imagine that as a wave in flavor space that will have different maxima and minima. And if you were to make that wave and keep it stable over a time that's long enough for you to measure it, then you might be able to simultaneously measure the flavor at one point and the flavor at another point, and you would see that they might be different. This is what you might call an instantaneous oscillation. It's similar to when you have a standing electromagnetic wave, for instance. Well, then you can do different measurements at different locations at the same time, and you would find that maybe at your first location, you're sitting on an oscillation peak, and in the other location, you're sitting on an oscillation dip or so. In that sense, that is probably what one would call instantaneous oscillation.
Okay, thank you.
All right. Any further questions at this point about neutrino oscillations? Because we are now going to move back to the early universe where we were headed all the time.
Yeah, I'm just curious why you introduced both the sterile neutrino and this right-handed active neutrino, I guess, or whatever you want to call it.
Just because it's simpler. If I want to have one sterile neutrino on which I focus as a dark matter candidate, and that can't be the same as the one that gives mass to the left-handed neutrinos.
I see. But in terms of neutrino oscillations, I can call this right-handed neutrino my sterile neutrino.
I would say yes.
Excellent. Thank you.
I've got a question about the Lecture1 experiment.
Yeah.
Maybe. So there we're measuring in the mass eigenstate, I assume.
Mm-hmm.
And we are sensitive to since we don't have any flavor changing instantaneously, we are measuring, or we only have electron neutrinos. Would we then expect 3 dips in the spectrum because we are dealing with different mass eigenstates? Or
Yes, exactly. So in a sense, in Lecture1, you're not measuring the neutrino, you're measuring the electron.
Yeah.
So in a sense, what's happening is a tritium tritium nucleus decays, and it produces a superposition of electron plus nu1, electron plus nu2, electron plus nu3. And for kinematic reasons, the electron state that would be produced with the nu1 is kinematically slightly different from the one that's produced together with the nu2. Now you are measuring this electron to an incredible precision such that you're able to break the superposition. And thereby what you're effectively doing so as the tritium decays, the neutrino propagates away as a superposition of the 3 mass eigenstates, but then you measure your electron. So in traditional quantum mechanical language, that collapses the wave function of the electron and the wave function of the neutrino into one of the 3 mass eigenstates. So say if you measure, if you were able to measure that you detect an electron whose energy is so high that it can only have been produced together with the nu1, but not together with the nu2, then by doing that measurement, you're collapsing also the wave function of the neutrino that is already somewhere in outer space back into a nu1 mass eigenstate. And in your Curie plot, this would show up as 2 kinks when each of the mass eigenstates gets switched off. In Lecture1, you probably won't have the resolution to see those because that would require you to have a mass resolution that's less than 0.1 electron volt. But in principle, if you were able to measure even more precisely, then that's what you would see.
okay, so in general, if we would see 4 kinks, this would be a hint towards the sterile neutrinos.
I think in Lecture1 there is even a search for sterile neutrinos, which is aiming for sterile neutrinos with somewhat heavier masses, where your resolution is sufficient. But that would require heavier sterile neutrino masses and relatively large mixing angles. And that's very hard to realize from a phenomenological point of view. That is typically ruled out by other things. But not entirely impossible. There are some Baroque models that achieve it. And those would then give you a signal, a nice one. Okay, so back to the early universe. Section 3, sterile neutrinos as dark matter candidates. Sterile nu as dark matter. So let me start by just making the statement that sterile neutrinos with a mass of order k, we have all the required properties to be dark matter. And tomorrow, when we are going to discuss constraints, we're going to see what those required properties are. So sterile nu at the KV scale have all properties required to be dark matter. Properties required to be dark matter. And that means notably they need to be cold enough, and they need to be sufficiently long-lived. But of course, there needs to be a way of making them in the right abundance. So the way of making sterile neutrinos in the early universe is what we're going to spend the rest of this lecture on, and perhaps also the beginning of the lecture tomorrow. So making new S sterile neutrino in the early universe. The mechanism in question is called the Dodelson-Wittrow mechanism. Dodelson-Wittrow mechanism. Then first going to give you a more intuitive explanation of what it does, and afterwards we're going to solve some equations to describe this physics more carefully. So the idea is we start with only active neutrinos. Start with active neutrinos only. So we assume that very early on after the Big Bang, maybe the decay of the inflaton or so has only populated the standard model sector, not the sterile sectors. We start out with a zero abundance of dark matter, and then we gradually freeze it in. So these active neutrinos start oscillating. So after some time has passed, there will be a still mostly active neutrinos, but there will be a small component of sterile neutrino. So each individual active neutrino acquires an admixture of a sterile neutrino, and the amplitude of that admixture is given by the mixing angle, 1/2 sine square 2 theta. Remember that the oscillation amplitude, just a moment, remember that the oscillation amplitude was sine square 2 theta here. And so if we average over those oscillations, then the average of sine square is 1/2. No, sorry. The average over the oscillating factor, the average over many oscillation periods, then the average amplitude will be 1/2 times sine square 2 theta. So if we give the neutrinos time to oscillate, a fraction of 1/2 times sine square 2 theta of them will have converted into sterile neutrinos. Yeah.
Why don't we want to start with a population of sterile neutrinos?
Because there would then be too many of them, and we wouldn't have a way of getting rid of them.
Okay, thanks.
Now, when the neutrino interacts, that interaction can be treated as a flavor measurement. The interaction will typically be a charge current interaction, so it will make a charged lepton of a definite flavor, so we can call this a flavor measurement. Once again, borrowing here the language of quantum mechanics from 100 years ago, which is no longer really the modern way we think about quantum mechanics, but it's perfectly suitable for this here. So this means the neutrino wave function collapses into either a purely active neutrino state or a purely sterile neutrino state. And the fraction of times it will collapse into a purely sterile neutrino state is, well, 1/2 times sine square 2 theta. So that means a fraction 1/2 times sine square 2 theta of all nu is now a pure sterile neutrino. Well, and then the neutrinos start oscillating again. Start oscillating again, and the whole process starts anew. So active neutrinos start oscillating again. After a while, they interact. This interaction projects them into one or the other flavor. And once again, we've converted a given fraction of them into sterile neutrinos. And after this happens many times, the sterile neutrino population gradually increases. And this is the gist of the Dodelson-Wittrow mechanism. This is how sterile neutrinos are made in the early universe. And I think that's perhaps the most central part of this lecture, these 4 items that I've written down here. Please.
Couldn't the sterile neutrinos also oscillate back into active neutrinos?
They could, but because there are much fewer of them than active neutrinos, that feedback is not important. This would be important if the populations of the two species were similar. But ultimately, in order to get the dark matter abundance that we observe today, the fraction of sterile neutrinos is only 10 to the minus 10 times the fraction of active neutrinos. So the few sterile neutrinos that oscillate back are a totally negligible effect here. Because half sine squared 2 theta of the full population of active neutrinos is a much larger number than half sine squared 2 theta of the small population of sterile neutrinos.
Okay, that makes sense. Thank you.
Yeah. But it's an important point, yeah. So any further questions on this? Yeah.
Maybe another question, but in this context, what does it mean that the wave function collapses? Because we are not, there is no one there measuring anything.
Okay, now that brings us to the more modern language of quantum mechanics. It means that the wave function of the neutrino gets entangled with the thermal bath that surrounds it. So somehow information that is initially stored only in the wave function of an individual particle is transferred onto the more or less chaotic ensemble of particles that surround this initial particle. And what this in particular means is because of the chaotic nature of the thermal bath, this erases any phase information that was contained in the neutrino wave function. And this is effectively what causes the collapse. Because in order to have a superposition, it means that different components of your superposition need to have well-defined phase structure. Once you randomize those phases, what it turns into is an incoherent ensemble of states. In a density matrix, I'm not sure if you're familiar with the density matrix formalism, but in density matrix language, this means that the off-diagonal elements of your density matrix get averaged to 0. And then you have a purely diagonal density matrix, which corresponds to a statistical ensemble, no longer to a coherent superposition. Sure. Yeah.
One more, thanks. Is there something that eventually makes this oscillation stop happening? Like, wouldn't the number of sterile neutrinos continually increase until the population of sterile neutrinos equal the population of active neutrinos?
The oscillations don't stop, but the interactions stop, simply because weak interactions freeze out.
Oh, okay, that makes sense. Thank you.
Yeah. Okay. Now, to describe the Dodelson-Withrow mechanism in a slightly more formal way, we need to involve a Boltzmann equation. Now, a Boltzmann equation is an equation for a phase space occupation number or a phase space density. That's a function that describes how many neutrinos occupy any given point in phase space. Here, for our purposes, we don't need to consider a full 6-dimensional phase space with 3 spatial dimensions and 3 momentum directions, because the universe is homogeneous and isotropic. So we are not going to consider any spatial dependence, and we're only consider a dependence on the neutrino energy, no dependence on the direction of their momenta because of isotropy. So then the Boltzmann equation reads as follows. I'm going to write it down and then discuss what it means. d over dt minus h times e times d over de f s of e and t is equal to 1/2 sine squared 2 theta. Let me call this theta m. That is a quantity that will depend on e and t. Times gamma of e and t, and the whole thing multiplied by fa of e and t. So just to set down the notation also here in the notes. So this is the phase space density of nu s. And this here is the same for nu a. So what do we have here? So on the left-hand side, we have one term that corresponds just to the time derivative of the occupation number of sterile neutrinos. That's like the thing that we are interested in. We're interested in how this changes over time. There's one term here that describes how neutrinos move from one energy bin to the other because of redshift. Because as the universe expands, the momenta of the neutrinos get redshifted. So they gradually move from higher energy bins to lower and lower energy bins. And the term of the right-hand side is a source term that describes how extrasterile neutrinos are added into the thermal bath by the Dodulson-Wittrow mechanism. The prefactor here, as you can see, is exactly this oscillation amplitude times the interaction rate. Well, and it gets multiplied by the phase space occupation number of the active neutrinos because they ultimately are the source. We are going to assume that this source is just a thermal one. So we are going to assume that FA is just a Fermi-Dirac distribution, E times E over temperature plus 1. So we're going to just, this basically means that we are neglecting this feedback that your question referred to. Otherwise, we would need to take into account that FA changes over time, but that change is totally negligible. So this gamma here, or let's first say this theta m. This is the mixing angle in matter. That's something we didn't go into detail on when we discussed neutrino oscillations, but when neutrinos travel through a medium, their effective mixing angles and mass spread differences change because they feel the effect of the medium through a process called coherent forward scattering. That's very important, for instance, in oscillations of solar neutrinos or supernova neutrinos, but we won't go into much detail on this here. Well, and finally, there's this interaction rate. These are just ordinary standard model weak interactions. So this is given by some prefactors, which I'm not going to derive here, but which happen to be 7 pi over 24. There is a factor G Fermi squared. That's because it's a weak interaction at low energy, so it can be described by Fermi theory. And then all weak interactions have to contain a GF squared. And there needs to be something that gives it the right dimensions. And in this particular case, this is a factor of temperature to the 4th power times the energy of our test neutrino, so to speak. Okay, yeah.
At what point in cosmological history is this happening?
Typically at temperatures around 100 MeV or so. Before that, not enough time has passed for neutrinos to oscillate. And then it goes down, it ends when neutrinos freeze out around the BBM time.
Okay, so just thinking about that theta matter parameter, so matter here would be like the plasma at early times, and then it'll evolve into something less dense at later times?
This is, since we're in a thermal plasma, this is a parameter that will depend on the temperature of the plasma, as I believe, I don't remember which power of the temperature, but it has a relatively strong dependence on temperature. And so it will gradually decrease as the temperature and the density decrease.
Okay, thank you.
Sure. Okay, so now final comment on this ansatz here, this first term here. This is obtained from considering that the total derivative of Fs of E, T is equal to, well, the partial derivative plus the partial derivative with respect to energy times the derivative of energy with respect to time. And then this dE over dt, this is exactly what gives you the Hubble factor. Well, because that's just how energies are redshifted. Over dt. is equal to h times e. So that's just how redshifting works. Okay. Now, I'm not sure if it still makes sense to start the next part of the derivation. I have 5 minutes left, right? Then I think it doesn't make sense to start the next part of the derivation. So I'll leave those 5 minutes for further questions, and I'm going to briefly tell you what we are going to do next. So in order to make progress, so basically this equation here, this describes how sterile neutrino dark matter would be produced in the early universe, but it's still a bit cumbersome. Sure, you could hack it into Python or Mathematica and have it solved numerically, and you'd get a beautiful result. But I'd like to make some progress analytically. And the way we're going to do this is we are going to integrate the equation over momenta. So integrating a phase-space density over momenta gives us just a spatial number density. So by doing this integral, we're going to turn this into an equation for the number density of sterile neutrinos. That will at first make it even more cumbersome, but then very soon it will collapse and will turn into a relatively simple equation, and that will become particularly simple when we then move from just the number density of sterile neutrinos to the ratio of the number densities of sterile and active neutrinos. The number density of active neutrinos is nearly constant, except for redshift. So by taking this ratio, we'll get rid of the redshift term, and we'll then get a very simple equation that is much more useful, and which will basically tell us what we already know, namely that the production rate of sterile neutrinos in co-moving coordinates is proportional to the interaction rate of neutrinos. And then having done this, then that will conclude our discussion of sterile neutrino production in the early universe. Then we'll talk about sterile neutrino decay. There I will not give you the full derivation. I will just show you the diagrams and then tell you the final result. And then we are going to look into phenomenology. So we're going to look at actual constraints that have been derived or can be derived from data. But that's for tomorrow. So for now, I'm happy to take any further questions now or over lunch. Yes, please.
In your last line here, when you have the change in phase space over time, d by dt of f.
Yeah.
I think you should have in the parentheses on the right-hand side, I think that dE should be a dt. You have d by dt plus dE by dt times dE.
No. What? This. Yeah. What I call dE here. Yeah, this should be a d over d. This should be a d over dE. Sure. Yeah. That's the wrong plan. Yeah, this should be a d over dE. That is makes more sense, right? Okay. Yeah, there's one 3 rows behind, 2 rows behind.
I don't quite get the role of this interaction rate. Gamma is just accounting for scattering of active neutrinos. So,
yeah, it's just the active neutrino scattering rate. This is perhaps a bit counterintuitive because you might argue, well, we are somehow here trying to do a flavor measurement. So we want to break the degeneracy between active and sterile neutrinos, but only the active neutrinos interact. So how can, in a sense, the non-interaction of a neutrino collapse it into a flavor eigenstate? And that's indeed a bit counterintuitive. Getting that come out of the equations automatically would require doing all of this in the density matrix formalism again.
And the second question, so the only reason why we don't consider this sterile neutrino dark matter to also account for neutrino masses is because we would never be able to detect in an oscillation experiment because the oscillation rate would be too small.
No, I think the mixing. So if you wanted to account for neutrino masses, you're thinking about a seesaw mechanism.
Yes.
Then the more or less known masses of the active neutrinos would determine the Yukawa couplings between the active and sterile neutrinos. And I believe with these U-cover couplings, they would need to be way too small to give you the mixing angles that you need to produce sufficient dark matter in the early universe. It's just different parameter regions that you need to explain neutrino masses versus explaining dark matter.
Thank you.
Of course, there are models that introduce both. So they follow the philosophy, well, if there's one sterile neutrino, there's probably several. And then one of them is the dark matter, the others account for neutrino masses and leptogenesis. That's, for instance, the so-called new MSM, the neutrino minimal standard model, is an example for this. This is like an attempt at a one-size-fits-all model, like solving all major problems of cosmology with sterile neutrinos at different mass scales. Okay, I don't see any further questions. I don't think there's any in the chat either. So yeah, we'll continue tomorrow at 9:30, I believe.
Yes.
Okay, then thanks a lot for your attention.